This video introduces a proofwriting technique called mathematical induction. There are a variety of proofwriting techniques that you'll learn throughout your mathematical career. We've seen proof by contrapositive when verifying whether a equation is one-to-one or not. So this is just another technique. So our principles of mathematical induction says if we let S sub n be a statement involving the positive integer n, if S sub 1 is true, so if our statement is true for the first term, and the truth of the statement S sub k implies the truth of the statement S sub k plus 1 for every positive integer k, then the statement S sub n is true for all positive integer n. So basically what's happening here is if our statement is true for our first term, if we assume that our statement is true for any general term, so that's the S sub k, kind of in the middle of all of our numbers, if that truth then implies that our statement is true for our next generic term, S sub k plus 1, then we can assume that it's true for every integer n. But sometimes math stuff works like once, maybe even twice. But if we can prove that it works generally, then it's going to work for all integer n. So here are our steps for mathematical induction. And it's going to sound more complicated than it really is. And the first one's going to seem very foreign when we do our first proof. But we'll see as we do multiple proofs that we're really doing the exact same thing over and over again. So we're going to let S sub n be a statement involving the positive integer n. To prove that S sub n is true for all positive integers n, it's going to require two steps. First, we're going to show that S sub 1 is true. Then we're going to assume S sub k is true, and from that show that S sub k plus 1 is also true. Then we can conclude that our statement is true for all positive integers n. We'll do one proof in this video, and then there will be a second video with a second proof. Let's prove that 3 plus 4 plus 5 all the way up to n plus 2, that sum is equal to n times n plus 5 divided by 2. When I write a proof, I like to write a lot of show lines, kind of just write out sentences to myself so I know what it is that I'm doing. I don't want to get lost in my proof. So I'm going to start my proof, and I just use PF to indicate that I'm starting my proof. The first thing that we need to do is we need to show that S sub 1 is true. So I always write a show line so I know what I'm trying to do. All right, well, to show that S sub 1 is true, we're simply going to plug 1 into this formula and see if we get 3, which is our first term there. So plugging 1 into my formula, we get 1 times 1 plus 5 divided by 2. It's 1 times 6 divided by 2. And we get 3, which is that first term. So we've shown that S sub 1 is true. Next, we're going to assume that S sub k is true. Well, what in the world does that mean? So I like to write a second assume line kind of explaining what that means so I know what I'm assuming in the first place. So if S sub k is true, then I'm assuming that S sub k, which would be equal to 3 plus 4 plus 5 plus k plus 2 is equal to k times k plus 5 over 2. So basically, I've just taken my original statement here, and everywhere there's an n, I've plugged in a k. So our assumed lines are things that we can take as fact. All right, so I've shown that S sub 1 is true. I've assumed that S sub k is true. And now that I need to show that S sub k plus 1 is true. So what does that mean? I like to write another show line kind of explaining what that means so I know what I'm actually trying to show. So that means that we're showing that S sub k plus 1 is going to be equal to 3 plus 4 plus 5 plus k plus 2 plus k plus 1 plus 2 is equal to k plus 1 times k plus 1 plus 5 all over 2. So basically, I went back to my first line up here, my given, and I replaced all the n's with k plus 1. Now, the only difference is I have this additional term, this k plus 2 term, and that's just the term before the k plus 1 term. That's our kth term. All right, I'm going to clean up this over here a little bit. So this would be k plus 1 times k plus 6 all over 2. So that's what we're trying to show. We're trying to show that S sub k plus 1 ends up being this over here. All right, let's do that. I'm going to start with S sub k plus 1, and I'm just going to rewrite this first bit right here, because that's what S sub k is. 3 plus 4 plus 5 plus k plus 2. And I'm going to go ahead and clean up this last term and make that k plus 3. Well, this here looks really familiar. That looks like this right here, which we assumed that is equal to k times k plus 5 over 2. So we are going to substitute, since this here is equal to S sub k, we're going to substitute k times k plus 5 over 2 in for that portion. K times k plus 5 over 2, and now we still have this plus k plus 3. We want to add these together. So I'm going to get a common denominator and a new numerator so I can add this fraction with the not a fraction. That's why I threw the not a fraction over 1. We're going to have to multiply this top and bottom by 2. And don't forget to distribute that 2. So k times k plus 5 over 2 plus 2k plus 6 all over 2. And now that we have our common denominator, we can go ahead and add our numerators together and put it over our common denominator. Now remember our goal. We're trying to get to this right here. I already have the 2 on the bottom, but the numerator certainly does not look the same. So we're going to multiply this out, combine like terms, and factor it, and hopefully we get that k plus 1 times k plus 6 over 2. If we don't, then the statement is not true. k squared plus 5k plus 2k plus 6 over 2. Combining like terms, that's k squared plus 7k plus 6 all over 2. And then we can factor our numerator into k plus 1 times k plus 6 all over 2. So now we go back and look, is that what we said we needed to show? We see that we've gotten to that green box, which is what we were trying to show in the first place. So this is true. Now we just need to write a wrap-up statement for our proof. We're going to say, therefore, by mathematical induction, and now we're going to write our given line, 3 plus 4 plus 5 plus n plus 2 equals n times n plus 5 over 2 for all integers n, positive integers n. So that's what this last little bit means. That upside down A means for all, that funny looking E means is an element of, boldface Z means integers, and the plus at the top means positive integers. If you wanted to write the words, that's fine, but in calculus, you're going to need to be using the symbols, so I would encourage you to get comfortable with it. So this says for all positive integers n. In the next video, we'll do another proof by mathematical induction.